Hi there, and welcome to Telefunken. Today's video is one of a series on the vintage Dynacord Echocord Super, model S62, an analog tube-based tape echo from the 1960s. Today, we will describe the parts needed to undertake one of the most common service steps when working with vintage electronic equipment. Yes, we're talking about replacing the machine's capacitors, a process commonly described as recapping. This video follows on from my introductory video, where I give a brief overview of the Echocord, show you what it's made of, including a brief description of some of the machine's capacitors. Capacitors are famous for failing, sometimes in rather spectacular ways. To add insult to injury, when a capacitor fails, they can, and often do, take out other components. In solid-state equipment, we might expect that capacitor failure could be a precursor to blown transistors or the like, destruction of components that are relatively easy to replace. However, in a vintage tube-based tape echo like this one, failing capacitors could be responsible for more serious consequences, such as the destruction of tape heads, oscillator coils, or even the power transformer, parts that might be difficult, if not impossible, to find replacements for. For this reason, because I'm refurbishing this machine for my own personal use and the pleasure and the experience of doing so, I'm going to take a rather comprehensive approach to recapping this Echocord and replace almost all of its capacitors. I'd describe the capacitors in the Echocord as being comprised of four main types or categories based on their construction. First, we have a number of electrolytic capacitors, which would be the first on our replacement list. This is because they're known to spontaneously degrade over time as their electrolyte either leaks, dries out, or they become electrically leaky to DC voltages. This category includes the motor run cap, a relatively rare, non-polarized electrolytic that might be hard to find a replacement for, as well as the power supply filter capacitors that provide a power reservoir in the DC power supply. Although some of the electrolytic capacitors in a vintage Echocord might test okay, most technicians would agree that they should be replaced as a matter of course as part of a preventative maintenance program, as they're going on 60 years old. Second on our list of candidates for replacement would be film capacitors, capacitors that are composed of layers of metal and plastic film. In the Echocord 62, these are made by the company Neocon and have a mustard yellow color. Although this type of capacitor construction is much more reliable than the paper and film types that predate the use of plastic films, they have been known to fail, though less frequently than their electrolytic cousins. Since proper testing of capacitors requires that they be removed from the circuit, I'm going to be replacing them wholesale on this machine in the name of future-proofing this equipment. There are plenty of people who would disagree with this approach, who might say, if it ain't broke, don't fix it. But again, I'm on a journey of discovery here. There are no bean counters or clock watchers involved, and replacing the film caps will give me an opportunity to comb over the rest of the circuit and make sure everything else is in good order. A third type of capacitor in the Echocord is actually formally and more properly characterized as another type of film capacitor, but this one is a polystyrene capacitor. There's only one polystyrene capacitor in the Echocord, and I'll be leaving it alone. There are a couple of reasons for this, not least among them the fact that they rarely fail, and this one appears to be working properly. The last of the four capacitor types in the Echocord are ceramic disc capacitors that you can see distributed throughout. These are the least likely of the four groups to fail. They're relatively accessible, but I'll be leaving most of them where they are unless I detect problems I need to solve later on, but that will be the subject of another video. So what capacitors will I need for this project, and where will I get them? Well, before I get started, I'll need to know which Echocord I'm working with. Sounds easy, right? Well, not so fast. Although the Super 61, Super 62, and Super 65 all look similar from the outside, they contain different electronic circuits on the inside. They're quite similar, but before ordering parts for your Echocord, you're going to want to make sure you're looking at the correct schematic. Even within the Super 62, there are at least 3 different versions of the Echocord circuit design. The Super 62 was released in 1962 with a build designation 76-101. Later, the circuit was revised. The 76-103 circuit incorporates modifications developed from 1962 to 1965, and the 76-104 circuit, also called the 62A, incorporates modifications developed over the same time period. It's possible that there is a fourth circuit, a 76102, but I've not seen evidence that such a thing exists online. The evolution of the Super 62 could be thought of as a gradual refinement in the circuitry that allowed for control and shaping of the tones of the echo, with the later versions having additional trimmers and adjusted capacitor values. Other changes included slightly beefier power resistors in the power supply. When developing a parts list for an Echocord, it's obviously necessary to determine which circuit you're working with first. My first step was to compare the circuit in my Echo to the schematics for the 101, 103, and 104 available online. My Echo appears to be a Super 62 76-101. It clearly has the S62 designation on the plate on the bottom. It lacks the additional trimmers on the top of the deck. So while the possibility exists that this Echo is based on the elusive 76102 circuit, since I don't have access to that schematic, I've based my parts list and rebuild plans on the 76101 schematic. The schematics that are available for the Echocord are scans of hand-drafted versions that are included in the various manuals you can find online. I personally found the parts designations and values very difficult to read, so I've generated a version of the schematic that I've relabeled and used for the remainder of the project. You'll see this version in some of my other videos, and I'll continue to annotate it with additional circuit descriptions and translations of the original German. My parts list is based on an examination of both the 76101 schematic and the Echo itself. This is necessary to validate the schematic, but also to make sure that any parts I buy are actually going to fit the device, both electrically and physically. One of the first things that will be apparent is that the majority of the electrolytic and film capacitors in the Echocord have axial leads, and while it might be possible to replace an axial film capacitor with a radially mounted one, it's going to be much more straightforward if I retain the original part geometry. Thankfully, there are a number of vendors that specialize in parts for vintage equipment, and one vendor in particular stocks almost all of the capacitors I needed, including the hard-to-find motor run capacitor. Frag Jan Zerst, which translates into Ask Jan First, specializes in parts for vintage tube equipment, including high-voltage electrolytics, high-quality film capacitors, and the motor run caps we need to rebuild our tape echoes. Frag Jan Zerst has a comprehensive website, great customer service, and it's one of those small businesses that you'll just love to support. I sent in an order to Germany and received my parts here on the West Coast in about a week. The few caps I was unable to find at FJZ were available on Mauser, an axial form factor, so I bundled these into my next Mauser order and I was off to the races. All in, my capacitor orders came to about $300 Canadian, or about $235 US. Other vendors that might be able to provide many of the parts needed to recap an Echo include Antique Radio Supply in the USA and Carl Capacitor King in Australia. The rest of this video includes a brief show and tell of what's involved in recapping the Echo. Some disassembly is required, however I'll spare you the details here. I'm also going to skip the actual process of recapping itself, as the desolder, removal, replace, resolder cycle might be quite tedious. For the most part, I replaced the capacitors one at a time, with the exception of some caps that were easier to get to once their neighbors were removed. The second part of the video will include some testing of the capacitors we removed from the Dynacord. We'll examine them using a variety of test instruments that are within reach of the average hobbyist, and this might give some comfort that this proactive approach to maintaining the Echocord is worth the trouble. A note of caution: this is not a small job. If you make a mistake here, you could destroy your Echo, or much worse, render it incredibly unsafe and actually kill someone, including yourself. If you're uncomfortable or don't know what you're doing, please leave this sort of thing to someone who does. If anything, this video may convince you to take your machine to a professional technician, which would be worth every penny you might pay to access their expertise. Without further ado, let's get started. Well, this is just an assortment of the parts that we have for the refurbishment of the Dynacord Echocord. And this is probably going to be the most extensive and expensive refurbishment of any piece of gear that I've ever undertaken. These capacitors are many of them are ordered from a gentleman in Germany who runs a small company called Ask Jan First, or Frag Jan Zerst, FJZ, and he sells capacitors for tube equipment. So for example, this is a 4.7 microfarad, 500 volt electrolytic capacitor, suitable for use in audio equipment. So I've obtained a lot of film caps and electrolytics from him, including, for example, this motor run cap, which is a 48 microfarad, 100 volt bipolar or non-polarized electrolytic capacitor. I've obtained new echo, or rather tape loops. I've obtained a used yet apparently functional playhead. One of the playheads is open. Obtained a number of other replacement electrolytic capacitors, sealed electrolytics. This, for example, again, a 470 microfarad, 63 volt. So not terribly special, but it is an axial and rather high grade, not terribly cheap. Lots of other capacitors, a few special power resistors and things of that nature in case anything is out of specification. And all of that ultimately is going to go in here somewhere. And I could set about to simply tear everything out and begin replacing components. But in advance of doing that, I would like to continue my diagnosis of this piece of equipment and, amongst other things, replace the non-functioning tape head with one that is working, and then begin to examine the performance of this equipment and identify whether or not there are any other problems prior to engaging in a wholesale refurbishment. And that way, hopefully, I can avoid introducing too many new problems and approach this in a reasonably methodological manner. So this is a bit of an update. What we have here is the Echocord, which has now been recapped. I've replaced all of the electrolytic capacitors, starting with the power filtering capacitor, the motor run cap, which is a bipolar, which is hidden here. You can't see it. It's underneath this assembly, and various other electrolytics distributed throughout the apparatus, and all of the film caps as well. The film caps are these now these black guys here, and a couple of the ceramic disc capacitors. The only capacitor that I haven't changed, or the only capacitors I haven't changed, are some of the ceramics and this polystyrene cap, which is sitting right here. I've also checked all of the resistors and replaced the power resistors, which were quite stressed and slightly out of tolerance. And I found another resistor that was out of tolerance right here. I have obtained a new socket for the power indicator light. The bulb was rusted into the kind of spring assembly socket that was stock with the equipment, and I'm going to be replacing it with a more modern one, which has just been glued onto this piece of phenolic, which was part of the original assembly. So that's what these two loose wires are here. And I have cleaned the switches. I want to point out one potential liability, which is this old diode here. It's an OA161 diode, which I've not replaced, but I did notice that when I was cleaning the PCB, I was using isopropanol, and some of the coating of this diode came off, and so it was slightly damaged by virtue of that cleaning process. If that reflects any internal damage, I'll check that out and see to it that I replace it with another OA161, which are available on the eBay market. They don't make them anymore, of course, but you can get original OA161s because they were so ubiquitous. I've also converted the selenium rectifier to a silicon rectifier, so there are now 4 diodes in here. And that is likely to increase the B+ coming from the diode to the filter capacitor, and that may require an adjustment on the value of these power resistors, but I'll check that once I've got the whole thing reassembled and we're powering the motor and heating the tubes and lighting the lights and so on. In the meantime, I'll flip it over so that you can have a look at the other side. This gives you a bit of a view of this switch assembly, which I did not actually remove. I didn't remove the switch assembly or the PCB, which they're essentially connected, but I did clean it very extensively with various contact cleaners, and it's now cleaned and lubricated. It was covered with a piece of fish paper, which covers these holes here and prevents dust from getting into the switches, and I'll be replacing that. Here you can see again the motor run cap and the magic eye tube and the lights for the switches. I cleaned up everything as best as I could, including the tube sockets and this ground wire. You can see here the ground actually runs on the outside of the chassis assembly and protrudes. The ground comes through, protruding through these little openings in the chassis, which have rubber grommets around them. These grommets are in reasonably good shape. I cleaned them up a little bit and put some armor all on them. Hopefully that won't damage them. And I also put new rubber grommets on the top where the heads will go. I'm about ready to reinstall the heads here and put all of this back together and begin testing. This represents a bit of a deviation from my original plan. My original plan was to remove this faceplate, and although that is possible, it wasn't necessary, and I was able to get access to everything, including all of these capacitors, all of these potentiometers, which I cleaned, every last one of them, without actually having to remove the faceplate. This is about as far as I can go without complete disassembly, which would be quite laborious, particularly this rear section, which, again, as you can see, because of these ground wires going through and being connected to all of the tube sockets and all of this stuff in here, taking all of this apart would be really quite the job, and I elected not to do that. You can probably see this a little better now, but you can see that all the penetrations where the grounding wires are coming through the chassis, and the tube sockets are, of course, all connected to all of that. There's this big bus bar here and another ground here, which is connected to all the input and output jacks. All of that would have had to be disassembled in order for me to completely disassemble the chassis. If, for example, I was going to repaint it. That's something I considered, but I elected not to do. So this was the approach that I took with this refurbishment. And very shortly we'll be at a stage where we can power it up and see how things work. So after going through all of that trouble to change the capacitors in the Dynacord, I thought it might be worth examining them and seeing how they test, how the old capacitors test relative to some of the expectations we might have for new capacitors. So we have the old capacitors here, including the main filter cap and the run cap, and some new caps to compare to. And the first test that I'm going to be looking at is the ESR, the equivalent series resistance. We'll just be using this cheap little ESR tester here. And what this does is it puts an AC signal, a low-level AC signal, through the capacitor. And this is a 100 kilohertz signal, and this will measure the resistance that 100 kilohertz signal is subject to. And ideally, we would want a resistance of 0, but practically there is an expectation that there would be some typical resistance associated with capacitors of different capacitance and voltage ratings. So we connect the negative lead to the instrument first, and then one of the positive leads. And we see in this instance, where we have a large filter cap of 32 microfarads, we have a equivalent series resistance that is, in this case, immeasurable. It's over 100 ohms. And that's not a good thing. We might be expecting a capacitor of this size to have a equivalent series resistance on the order of maybe 1 ohm, ideally even less than that. Maybe 2 ohms at the most, but certainly not 100 ohms. We look at the other leg, the other capacitor embedded within this. Again, we can't measure the equivalent series resistance in this capacitor. So let's have a look at another capacitor. This is a replacement capacitor, and I believe this is the negative terminal here, and this is one of the positive leads, if I'm not mistaken. We see a resistance of 1.35 ohms on this capacitor, which is essentially a drop-in replacement. It's 32 microfarads, and this is a 550 volt capacitor. If we look at the other leg of this capacitor, or the other section of this capacitor, we again see a resistance of about 1.18 ohms. So the power supply was trying to get AC voltage through this capacitor at a resistance of 100 ohms. So no wonder this capacitor was showing some signs of failing with electrolyte leaking out of this little vent on the top. So what about this capacitor? This is our 48 microfarad motor run cap, and this is not a polarized capacitor. This is a non-polarized capacitor. And we see a very low equivalent series resistance, which is great. So low, in fact, it leads me to suspect that might be shorted, but I can have a look at that later. How about some of these other capacitors? This is similarly a 32 microfarad cap. This is not the motor run cap, but rather this is one of the capacitors that is part of the power supply filtration. It's 0.65 ohms, very low, and if we can believe this, this is certainly acceptable equivalent series resistance. How about some of these other electrolytics? Well, we have these 4 microfarad 350 volt capacitors, and we'll see how they test. This one's 1.37 ohms, and it's really fine. That's a very good value for this capacitor. We'll look at this one, which is essentially an identical capacitor. However, we see that its equivalent series resistance is greater than 100 ohms. So these capacitors, which from the outside, well, they're the same capacitor essentially. They look almost the same. If any, well, I don't see any real bulging or obvious leakage of electrolyte. This one maybe has bulged a little bit because the label has peeled off a little bit more than it has off of this one. That might be the only hint that this one was subject to some sort of stress that this one was not subject to. So this one tests fine. This one tests quite poorly. Some other examples. Let's look at these little guys. These are 50 microfarad, 15 volt capacitors. And we have 3 of these in the machine. If we look at this first one, we see an ESR of 2.39, which is, for this capacitor, a little on the high side. Ideally, it should be below about 1.6. If we look at this one, we see an ESR of, well, it's too high to measure, so this one is no good. And if we look at this one, oops. We see an ESR of 2.16. And we have an extra one of these replacement capacitors. This is a Chemet electrolytic. It's 47 microfarads at 25 volts. So it's a little higher voltage, and it is roughly equivalent capacitance, a little lower. But we see its equivalent series resistance is 0.119 ohms. And that's what we want in this instrument, is very low ESR electrolytic capacitors. And these are what have been used to replace these. We had fairly high ESR in 2 of them and absolutely off scale with another one. So examples of capacitors failing in terms of their equivalent series resistance. Now, we also have all of these film caps. Here's an example of a 0.05 microfarad. And what's the ESR on this? Well, this is a very different capacitor construction. And we would expect a different type of equivalent series resistance. This one we have 24.4 ohms. And if we find an equivalent, assuming I have one here, an equivalent new one, and we do, let's see what this guy looks like. We see it's 31 ohms, so it's actually a little higher, and that's not entirely unexpected. We expect these types of capacitors to have a higher ESR than our electrolytics. So again, that's an acceptable result. So whether or not these particular capacitors warranted replacement on the basis of high ESR or not remains to be determined. I haven't gone and tested all of them, but there are other reasons for replacing capacitors, including this type of capacitor. And that could be that they have the potential to become electrically leaky rather than increasing in ESR, or rather than leaking electrolyte, they can become electrically leaky, where they fail to protect from the passage of DC voltages. So that's a different test. It is not going to be performed by this particular device. We require the use of a different testing device, testing technology, in order to determine whether or not capacitors are electrically leaky or not. So this is a very different kind of capacitor tester. This is a so-called IT11 made by Heathkit. This is made from a kit, and it is a capacitor tester that is favored by enthusiasts who like to rebuild vintage radios and the like. And one of the reasons why people like it is it has the ability to test for leakage under high voltages. The voltage here can go up to 600 volts DC. And so first thing we're going to do is we're going to take a look at this capacitor, which is a 50 nanofarad capacitor, and we're going to measure the capacitance using the bridge feature. We're on the C times 0.01 setting on the dial, and we read the capacitance off of this second scale here, capacitance C scale, and multiply this value times 0.01. So a 50 nanofarad capacitor, we might expect to see the capacitance reading measure at 5 times 0.01 is going to give us a value of 50 nanofarads. So the Magic Eye tube is currently closed, meaning that there's green all the way around. And in fact, the two green areas are overlapping. As I increase the capacitance value on the dial, and we approach the expected capacitance value of 50 nanofarads, represented by this 5 here on the scale, we begin to see a black opening appear at the bottom of the Magic Eye tube. And that indicates to us exactly how much capacitance is in this capacitor. And you can see it just begins to open as we pass 5. Just begins to open as we pass 5. And if I continue to rotate this dial, it opens and then shuts again. So we have a capacitance in around that range, maybe 55 nanofarads or so. Okay, so let's quickly switch this off, change capacitors. This is also a 50 nanofarad capacitor. This is an older one, taken from the Dynacord. Turn the instrument back on. Let it warm up until the Magic Eye tube is fully illuminated. And we'll measure the capacitance here. Well then, the capacitance on this capacitor appears to be much higher than 50 nanofarads. I'll change the scale here. Whoops. And we see the eye opening around 1 microfarad. So if we're to believe this, we have a capacitance in this capacitor that approaches 1 microfarad. Turn this back down. I'll remove this capacitor. If we evaluate the capacitance of this capacitor using this more modern testing device, it's giving us a value of 68.2 nanofarads. Let's just make sure this is calibrated properly. And it is not. There we go. .2 nanofarads. So let's come back here, see what's going on. See if we just had a bad connection there. We're again back on the 0.01 scale. We'll increase this. Oh, I am seeing a little deflection right around that point. Okay. So the other test we can perform on this type of capacitor is a leakage test. And the way we do that is by moving the tester to the leakage scale, and we're on paper, mica, etc. setting, which is the most stringent. And as we increase the voltage using this voltage scale, what we're doing is we're applying a DC voltage to the capacitor. So currently we're at 6 volts, and you can see the magic eye is open. It's a little dim. It closes and it opens, 10 volts. And as I turn this again to 15, it'll close and open. Closes and opens. And each time it takes a little longer. It's at 50. And it's very slow in opening. It hasn't opened yet. What this represents is leakage, voltage leakage at a voltage of 50 volts. There it's open. Now we have 100 volts on this capacitor, and the eye has not opened. This capacitor is rated at 500 to 1500 volts, and yet it's leaking at 100 volts. So this is obviously a leaky capacitor. Turn this down, discharge the capacitor by putting this on the discharge setting. Let's have a look at another one of these capacitors, rather a new capacitor. I thought I had marked the foil on each of these, but I don't believe I can see it on this one. So we're on discharge, and we're at 3 volts. So starting at 3 volts, the eye is very quick to open as we go up in voltage, 100 volts, 150, 200, 250, 300, and it keeps on opening. And what this is showing us is that there is all the way to 600 volts, and we have an open eye here. This capacitor is not leaking DC voltage, even at 600 volts. We have 600 volts on this capacitor, so we want to be very careful what we do with it. So we move the instrument setting to discharge, and this allows this capacitor to discharge through a resistor. And thereby keeping us safe. So this is another example of a test, a different test for the function of a given capacitor that we can perform to evaluate whether or not the capacitor is working as it should. And in this case, even though this capacitor had an ESR that was just fine, this capacitor is testing on this instrument with a capacitance that's acceptable. It is not acceptable from the perspective of leaking DC voltage. What should we test next? Why don't we have a look at, actually, why don't we have a look at these guys? Let's look at these guys because we know we have a comparable. Actually, we have these. So these two capacitors are electrolytic capacitors, 4 microfarads, 350 volts. So if we connect these and set this to the bridge setting, we're on C times 1 scale. We're going to attempt to measure the capacitance of this capacitor. It's supposed to be 4 microfarads, and so we should see the magic eye open and close around 4 microfarads. And there it is. It is maximally open around 5 and begins to open at about 4.9 or so. Okay, well, how does it perform on our leakage test? And this is the capacitor that had an adequate ESR. So this is a 350 volt capacitor. So we set this to electrolytic, and this gives different tolerances in terms of the amount of leakage that's acceptable when compared to a paper or mica capacitor. At 3 volts, we have an open eye, 10, 100, it begins to flicker closed, 150, 200, 250, 300, and it's open. And I'll go to 350, and it's open. So this capacitor tests okay in terms of the ESR. I'll turn this to discharge. The ESR, the capacitance, and the leakage. So what about its counterpart? This is now discharged. I can remove it from the instrument. We have to make sure we incorporate the capacitor under test in the appropriate orientation because it is getting polarized DC voltage. So we'll measure its capacitance first. We're expecting about 4 microfarad. And our eye wants to open way down here, which is below 100 nanofarads. So I will change the scale, and we see so we have a much lower capacitance than we expected. If we go to the leakage test, we're at 3 volts. This is a 350 volt capacitor. Going to discharge this capacitor. with this instrument, this capacitor measures with 0. It measures around 5 nanofarads. Yes, this capacitor is measuring around 5 nanofarads, which might explain why it didn't give us a good reading on either scale. So I'll go right down to this scale and see if that agreement, if we get agreement, if we're expecting a capacitance of around 5 nanofarads. The magic eye is open. We're on the 0.0001 scale, and so we would want to see the eye open around 50, or close rather around 50 for 5 nanofarads, and we're not quite seeing that. So this is no longer acting. Oh, we weren't on the appropriate setting. We were on the discharge setting. So I'll go up to 5 nanofarads. Oh, there we are, right around 5. Yeah, so around maybe 60 nanofarad, 6 nanofarads or so. This instrument says this capacitor, which is supposed to be a 4 microfarad capacitor, has a capacitance around 6 nanofarads. Another reason why we might want to leave this out of our circuit. Again, we'll evaluate the leakage, and it does not appear to be leaking. Oh, there we are. Yeah, at higher voltages, 350, it's leaking. $300, it's okay. 350, it's leaking. So leakage isn't its problem, it's lost capacitance. That's its problem. And it has a very high ESR, one that cannot be measured. So that's why this capacitor is no good. And again, let's compare it to this one. It had a very low ESR, much lower than 1. And we'll put this in the bridge configuration. This is in this case, we're looking at a 47 microfarad capacitor, which would be a replacement for these small silver capacitors. This is a 25 volt capacitor, 47 microfarads. And if it's 47 microfarads, we go to the ×1 setting on the C scale. And if we increase we see that eye open right around 50, a little above 50, corresponding to the value on the capacitor. So it's in the approximately correct range. We'll put it in the discharge position, put it in leakage and do a leakage test. Keeping in mind, again, this is a 25 volt capacitor, so we won't go too high on the leakage test. It's wide open at 6 volts, wide open at 10, 15, wide open at 25, and I can double this by going to the next step, 50, and it stayed wide open. Even though this is only rated as a 25 volt capacitor, it is completely leakage free as measured by this device in the electrolytic capacitor setting when we apply 50 volts to it. So again, very robust capacitor, which you would expect because it's a brand new chemat capacitor. Let's compare to one of these guys. This is a 50 microfarad capacitor. It's 12 and 16 volts. So we're in the capacitance test position, and we see approximately maybe 60 microfarads. Put this in the discharge position, then go to leakage test. And as we increase the voltage, at 15 volts, the eye is still open, indicating this is not leaking. And then it begins to flicker shut around 25 volts. And that's about what we might expect. I believe this is the capacitor with the reasonably normal ESR. Let's come back to one of these others. One of them was completely unacceptable. I can't recall which it was. Measure this one. This one again is about 50 to 60 microfarads. Its leakage is fine, up to 25 volts. Oh, no, we're in the discharge position. We see a bit of a flicker at 25 volts. But again, it would pass the leakage test. How about this next one? We're measuring its capacitance. And again, its capacitance appears to be adequate, in between about 50 and maybe 60 microfarads. Go to the leakage test. 15 volts. And a little bit of a flicker at 25. Again, we won't go higher. This is a 12 and 15 volt rated capacitor. So these three capacitors, in spite of one of them having a very high ESR, tested fine on the leakage test. So again, it's necessary to evaluate capacitors from more than one perspective when we're considering whether or not they require replacing or not, because they need to be out of circuit to be tested properly. I deemed it to be most expeditious to simply replace wholesale all of the electrolytics, all of the film caps, and some of the ceramic capacitors in the Dynacord. And hopefully these demonstrations have gone some way towards explaining my particular approach to recapping the Dynacord, but feel free to leave comments and suggestions in the comments section of the video if you have different approaches or different ideas about how to tackle this problem. Well, that's all the time we have for today's video. Future episodes in this series will cover the disassembly and servicing of the Dynacord, reassembly, and the potential for modifying the machine's tape speed. I hope you've enjoyed this video. Thanks for watching.